Today we're going to talk about linear programming. But before we do that, I wanted to talk about one thing that appears in the book in section 4.3 or 10.3 in the Kindle edition, and that's about invariance of a game under scale and location. We've kind of talked about at least a big part of this before, so let me explain what I mean. We've already said if you have a matrix A for some finite game, and you take each entry in the matrix and add some number, in this case that's the number b here, to that entry, that behaves functionally in the game as if you play the game as it originally was, and just player 2 pays player 1 this extra side amount b no matter what happens. That's what happens if you add b to each and every entry. There's just an extra b as a payout no matter what. Naturally, with this extra payout, that doesn't change how the two players will play the game. So the value of the game will stay the same without this extra payout. With the payout, the value of the game just increases by b. A second type of modification to the game would be multiplying each entry by a positive constant c. And here it's very important that this constant c be positive. Imagine you just double the payout of every entry in the game. The idea is that it should be pretty clear that that doesn't change the way people play the game. The optimal strategies will be identical, just whatever the payouts were before, they're double now. Whatever would have been an optimal strategy before is still optimal. Why is it important that C be positive? Well, of course, if C equals 0, that just zeroes out the game, and you're not getting any information there about how the game plays. And if C is negative, that changes the game substantially, because player 1's trying to maximize his return. For example, if you multiply every entry by a negative constant, now all of a sudden what was good is bad, and vice versa. Things do change a lot. But if you multiply each entry by a positive constant, the gameplay doesn't change. What will happen to the value of the game if you multiply every entry by 3, for example? That should just triple the value of the game. Whatever happens, you're going to win 3 times as much if you're player 1, or pay out 3 times as much if you're player 2 and paying out a positive amount to player 1. So we can put that together in a theorem that says if we start with the matrix A for the game, and we have a new matrix A prime, where each entry of A prime, the ijth entry, is just C times the ijth entry of A, plus this constant B, again where C is positive, then the game with A has these exact same minimax strategies for both players 1 and 2 as a game with matrix A prime. Also, if V is the value of the game for matrix A and V prime is the value of the game for matrix A prime, then V prime will just be, as we've seen before, the constant C times V plus B. Now let's really get started talking about linear programming, because this is really what we're going to need to do to talk about solving general finite games. And I'll show you how linear programming works with an example of a problem and its dual. A linear programming problem is one where you want to maximize a function called the objective function. In this case, that function will be a function of 2 variables, x1 and x2, but in general it could be a very large number of variables. So this is our objective function. I'll use x1 plus 7x2. And we want to maximize that function subject to some constraints. These conditions we refer to as the constraints. And these constraints should be linear inequalities. It's important that everything be linear, of course. This is linear programming. And the constraints should be inequalities. So if you graph these, the graph of a single linear equality is just a half plane here in 2 dimensions when you have only 2 variables. If you have 3 variables, it would be a half space, meaning a half of 3-dimensional space. And these are always going to be inequalities of the form less than or equal to. So it would, in 2 dimensions, it'll contain a line and the half plane either below or above the line, and this depending on the signs here of the entries. And in 3 dimensions, you'll have a closed half space. In 4 dimensions, you can see things will be getting much more complicated. And in general, for a linear programming problem, even if you have only 2 variables, you can have any number of constraints. Here I've only put 2. Minus x1 plus x2 is less than or equal to 1, and x1 plus x2 is less than or equal to 3. And typically we'll have this normalizing condition that our variables always have to be greater than or equal to 0. we'll set it up so that that's the way things work. Now, in this very simple case, when we have two variables, a simple objective function, of course, and only two constraints, it's very easy to tell what's going on just by graphing everything. So let's do that. Our normalizing condition here, that x1 and x2 are greater than or equal to 0, says everything will take place up here in quadrant 1. And of course, we'll include the positive parts of the x1 and x2 axis. Here will be the x1 axis, here will be the x2 axis. And then we'll just graph these constraints. If we graph minus x1 plus x2 equals 1, well, what does that look like? That looks like a line like this in the x1, x2 plane. And where's the region where minus x1 plus x2 is less than 1? Well, that would be one side of this line. It's pretty clear that when you make x1 bigger, meaning go off to the right, or x2 smaller, go down, that will make the left side smaller. So really we have this half plane. Remember, our condition that x1 and x2 are greater than or equal to 0 means we're always here to the right of the x2 axis and above the x1 axis. So we have kind of this region. I'll just graph the entire thing here. This entire half plane is the graph of this one constraint. The second constraint, x1 plus x2 is less than or equal to 3. I can graph x1 plus x2 equals 3. Let me get rid of this. Something like that. Here's the point 3, 0. Here's, 0, 3. Here's the point 0, 1. Here's 3, 0. Like that. And where do we have x1 plus x2 less than or equal to 3? That will be, if I pick a different color here, down on this side of that line. And now if we look at the region where both of these are satisfied, that's the intersection of these, and if we include our condition that x1 and x2 are greater than or equal to 0, we see that the region we're interested in is here. This is our active region. And the goal is to maximize this objective function for all points in this region. And remember, it's a closed region. It contains these line segments here and everything inside. Here's my claim that's true here, and it's also going to be true in literally any linear programming problem. I claim that the point where the maximum value of our objective function occurs must be at one of these vertices, some vertex of the active region here, the allowable region. Why is that? Well, if I graph x1 plus 7x2 equals c for just an arbitrary constant c, what does that look like? Well, the answer, of course, is that it looks like a line, and you can easily see that the slope of that line here is negative 1/7, and so here would be a typical line like this, a very shallow slope. And if I increase c, that just kind of moves the line further out. And we want to know the maximum value for this function. In other words, the maximum value of c we can get from some point in the active region. Well, we'll just keep going. These should actually be a little bit less steep. These should all be parallel lines, but a little less steep than the ones that I'm drawing. The slope should only be negative 1/7. There'll be one of them here that goes through that one vertex, and you'll see that that's the one with the biggest possible value for c. And however you draw this line, as you move it upwards, increasing the value of c, the highest point it touches is one of these. Now, it doesn't have to be that one. If the line has a very different shape, just hypothetically here, if I draw very different shaped lines, say very steep lines like this, you see that maybe the highest value of c occurs at this vertex. Or if there were negative signs on things, it might be down here at this vertex. It could, in principle, depending on the objective function, be any one of these vertices, we see that for the problem we have, it's at this vertex right here. And it's easy to see that comes at the intersection of these two lines, minus x1 plus x2 equals 1. And I didn't draw the equation here. This line is the x1 plus x2 equals 3. And it's easy to find the coordinates of that point of intersection. That's the point 1, 2. You can easily see that that is where these two lines meet. We have the other vertices here, 0, 1, and 3, 0. And of course, this is 0, 0. So graphically, we kind of know that's the point where our objective function is maximized. We have x at that point, x1 plus 7x2 is 15. So I claim the maximum of x1 plus 7x2 subject to these constraints is 15, and it occurs at this point 1, 2. Now let's say that the graphical situation was such that you really couldn't draw it nicely. Is it easy to solve the problem anyway? Well, yes, you can just plug in every one of these vertices and check the value of your objective function at each one. At 0, 0, obviously the objective function is 0. At 0, 1, it's 7. At 3, 0, it's 3. And of course at 1, 2, it's 15. So one way you can solve a linear programming problem like this is to look at every vertex here, and the shape that's made here is called a simplex, and here we have only these 4 vertices, so it's very easy to plug in every possible value and see where the maximum occurs. Just see which one's biggest. Here's the problem with that. If you have a huge number of variables, and in many linear programming problems, say when you're modeling a business with 100 different factors, and you could have 500 different linear inequalities, each representing some aspect of the business that must be satisfied, then the number of these points of intersection here in a 100-dimensional space could be ridiculously huge. But in principle, this should get you the answer. You just find all the vertices and plug them in, find where the objective function is maximized. Now, before we talk about further things, let's talk about a related problem. I'm going to look at what we call the dual problem to the problem above. And let me remind you of the problem above over here that we already looked at. It's said to maximize. We had x1 plus 7x2. And here were the inequalities. They were minus x1 plus x2 less than or equal to 1. And we had x1 plus x2 less than or equal to 3. And of course, we had our normalization conditions here that x1 and x2 were greater than or equal to 0. Now, this will seem strange at first, but if you look at these coefficients, negative 1, 1, and the coefficient on our objective function, 1, we're going to change that into a new constraint with new variables y1 and y2. This new constraint will look like minus y1 plus y2 greater than or equal to 1. We've switched the inequality now from the previous problem where they were less than or equal to's to now greater than or equal to's. In the next column, we have 1, 1, and 7, so we're going to write down y1 plus y2 greater than or equal to 7. And notice we had our objective function here, x1 plus 7x2. Now our objective function will be y1 plus 3y2. We'll look at these constants that were on the right side of our linear inequalities in the previous problem and turn that into a new objective function. So we have new variables y1 and y2. These are our dual variables. Those will have to be greater than or equal to 0, just as before. And we have a new objective function and new linear inequalities. We want to minimize this new objective function, and our inequalities go in the other direction. Let's see what happens when we try to solve this problem. In our new picture, we have the axes for y1 and y2. Again, saying y1 and y2 are greater than or equal to 0 means we're going to be in the first quadrant here. Minus y1 plus y2 greater than or equal to 1 looks like this now. where here's the point 0, 1. But now we want minus y1 plus y2 greater than or equal to 1. So let me put, let me shade in the appropriate half plane here. That would be this one. Things get bigger if you let y2, for example, get bigger. Let's look at y1 plus y2 greater than or equal to 7. This line, by the way, let me write down minus y1 plus y2 equals 1. The y1 plus y2 equals 7, if I just extend this a bit more, looks something like this. Where here's the point 7, 0. This is y1 plus y2 equals 7. And here's the point 0, 7, way up there. Maybe I made it too high, but that doesn't really matter. And the half plane where y1 plus y2 is greater than or equal to 7 is the one that's above there. The intersection of these, and again, remember we're staying in the region where y1 and y2 are positive, looks like this. It has to be to the right of the y2 axis. If I extend this line out a bit. So it has to be this red region, which you see extends off to infinity here. But our goal now is to minimize this objective function. And I claim, just as before, that the minimum has to occur at one of these, use green here, one of these vertices. In this case, there are only 2 vertices with this simplex. It extends out to infinity. This is the vertex 0, 7, and this is the vertex, when those intersect, it's the vertex at 3, 4. So let me write that in here. And we can just plug those in to our objective function and see at 0, 7, we get 21. At 3, 4, we get 3 plus 12 is 15. And we're trying to minimize the objective function. So my claim is that the minimum of y1 plus 3y2 in this allowable region, that means subject to these constraints, is 15. Now, you might recognize that this number 15, which is the minimum of this objective function, was exactly the same as the maximum of our previous objective function. In other words, these 2 problems, our original problem and this strange new one that we created as what we'll call the dual problem, have the exact same solution. And even though you might think that's just a coincidence here with very simple linear programming problems, that's something deep and pretty amazing about linear programming, that any problem, properly phrased linear programming problem, has a dual problem. Both can be solved and will have the same solution. At least when one can be solved, the other one can, and they have the same solution, which is a really amazing thing.